My pleasure to introduce Dr. Thall today. He's a professor at MD Anderson in biostatistics and really a pioneer in Bayesian statistics. He's written over 260 papers, including 2 textbooks as well on these topics. So for our next installment here, the Biostatistics and Evidence Appraisal seminar series, this is going to be a little bit more advanced, but hopefully it'll teach us the basics of Bayesian statistics. I know this is an area that I struggle with and many do as well. So Peter, take it away. The stage is yours.
Okay, thank you. So here's the title, Bayesian Clinical Trial Design and Data Analysis in Oncology, rather general. It's hard to know how to organize a talk like this, but it's not just recommended, it's required meeting. Everybody really should buy a copy because I desperately need the money. But seriously, I wrote this for readers who are not statisticians, readers who actually are physicians that use statistics or work with people that use statistics. So I think it's a useful book. Here's the outline. I'm going to go through some elements of Bayesian statistics just to give a platform for the rest. And then I'll talk about quantifying strength of evidence and get into what's wrong with p-values. Then I'm going to go through 4 specific examples. The radiation dose, phase 1/2 trial, and then we'll talk about precision medicine, subgroup specific effects in a randomized trial of nutritional rehabilitation for postoperative morbidity. And then something we've worked on for 20 years, personalizing pharmacokinetically guided intravenous busulfan dose in allogeneic transplant. Then if I have time, I'll talk about a randomized pilot study that we're doing now. So here are the elements of Bayesian statistics. And this formula is the most technical thing probably that I'll have. In a Bayesian model, there are actually 2 objects. One of them is data, the other is parameters. And parameters play a central role. I'm using the Greek symbol theta to represent 1 or more parameters in a model. And Bayesians consider parameters to be random. So we give them a prior probability distribution. And this is based on belief or previous data. So the prior may be informative if you've got data. If it's not informative, you use, well, a non-informative prior that has an effective sample size of 1 or something like that. And theta doesn't need to be abstract. It includes things you're very familiar with conceptually. They're things like the probability of response, median survival time, treatment effects on outcome, or covariate effects. So Bayes' theorem allows you to invert probabilities. So the likelihood of the data given the parameter vector is something like a binomial distribution or a normal distribution and so on, depending upon what your data structure is. If you multiply that by the prior and then you norm it by the probability of the data, then you actually reverse the probability. You get the probability distribution of the parameter vector given the data. And so what Bayesians do is mine the posterior for information to do inferences about theta. And I'll get to that. So Bayesian learning is something that you do sequentially. So, and this is what people do in their lives every single day. The things that you did this morning were actually Bayesian learning, but you've been doing it all your life and you don't have a formal model. So as data are obtained, as data are obtained sequentially in a clinical trial, you apply Bayes' theorems repeatedly. So you get data, you compute the posterior, you look at it, then you take another action, you get more data and you repeat, but each time you use the posterior from the previous stage as the prior for the next stage. So here's some pictures of beta distribution. So one thing that Bayesians can do is draw pictures of the probability distributions of these parameters. And I'll talk a lot about the beta, which is a prior distribution that's used for probabilities. So let's say that theta is just one thing. It's the probability of response. And in the upper left-hand corner, I've got a picture of something very non-informative. It's a beta with parameters 1/2, 1/2. And you see it's U-shaped. Its mean is 0.5, but the effective sample size is 1. It's not informative. If you go to the upper right, you've got a beta distribution that also has mean 0.5, but its parameters are 3 and 3, and you see it's getting a bit more informative. For a beta 4.2, the mean is 2/3, And you see now the effective sample size is 6, the same as the one in the upper right. In the lower right, we've got a beta 912. There, the mean is 0.75, and you see the effective sample size is 12. As the effective sample size of the beta goes up, it becomes more and more informative. And so let's get to a particular example of why one would want to use Bayesian statistics at all. Here's the theta is the probability of toxicity of some experimental agent at a fixed dose, say in a phase 1 trial. Just suppose that you observe some number of toxicities, I'll call it X, in 3 patients. The question is, how do you estimate theta? How do you estimate the probability of toxicity? So the usual frequentist estimator is something that everybody knows. You take the number of toxicities and divide it by the sample size. So in my notation, it's X divided by 3. And if you look at the possibilities, it can be 0 out of 3, 1/3, 2/3, and so on. Here they are in decimal form. But the estimator really doesn't make sense. Because if you get 0 out of 3, what you're saying is, I estimate that the probability of toxicity equals 0, which says that you believe that toxicity is impossible, which is really ridiculous. And then if you get 3 out of 3, based on this tiny sample, you say, I estimate that the probability of toxicity equals 1. So it says you believe toxicity is certain, also ridiculous. So let's suppose that in reality, so God whispers in your ear, or the universe whispers in your ear, that the true value of theta is 0.2. Let's assume that's true. And if that is true, then the probability of observing 0 toxicities in 3 patients is over 1/2. You're more likely to observe 0 out of 3 than anything else. So in words, is that if the probability of toxicity actually is 0.2, based on a sample of 3 patients, there's a 51% chance that you will estimate theta to be 0, equivalently that you will say toxicity is impossible. It's silly. So you could say, well, wait a minute. What if you use a 95% confidence interval to account for the large variability in the small sample? So if you go to your typical statistical textbook and look up the formula for a 95% confidence interval for binomial data, you'll see that both the upper and lower limits are 0. So you get a confidence interval that's ridiculous. So how do we get out of this mess? Well, here's the Bayesian analysis. So theta is random to a Bayesian. We give it a prior. So let's give it that beta 0.5 prior, which says, as I mentioned before, well, the mean is 0.5, but the effective sample size is 1. So it's not really informative. So if we turn the crank and apply Bayes' theorem, the beta has this very nice property that with the binomial distribution, where you're counting toxicities or counting something, the posterior is also beta, it's conjugate. And all you're really doing is adding the number of responses to 0.5 and adding the number of non-responses to 0.5 for the second parameter. And if you go through the process of computing the posterior mean of that beta, you get this weighted average. It's 0.5, which is the prior mean weighted by 1/4. And it's the usual sample mean weighted by 3/4. And what this does is shrink or pull the usual estimate x over n toward the prior mean 0.5. And there's this general saying that a little bit of shrinkage is a good thing. Here's why. Here's a table giving the from 0, 1, 2, or 3 toxicities, the usual estimators that you get. I've called them sample mean in red, and then the posterior mean of theta in blue. And you see, and I've also given posterior 95% credible intervals in each case. Of course, they're very wide. A 95% credible interval, LU, is a pair of numbers such that the probability that the parameters between those limits, given the data, is 0.95. And if you ask 100 people to define confidence interval, this is probably what they'll say, but that's not what a confidence interval is. The definition of confidence interval is very strange, actually. So what's going on here is, instead of the ridiculous estimator, you've got an estimator that says, well, on average, we would estimate the probability of toxicity to be 0.125 if we observe 0 out of 3. It's more reasonable, but we've got quite a bit of uncertainty. Now, if they had applied this, when you've got very large, a very small sample, but the consequence of getting one event out of 3 is a multi-billion-dollar disaster, as we just had in Texas, it makes a lot more sense because you'll prepare for it, but they didn't. So here's how this works. The Bayesian practice of assigning small prior probabilities to rare events avoids allowing an observed zero count to lead to the frequentist estimator that is zero, that says the event is impossible. And this has been applied many times, applied to identify rare diseases, identify rare species, solve problems in cryptography, which is code breaking, at the National Security Agency that probably shortened World War II by about 2 years. Estimate probabilities of rare but catastrophic events like 2 airplanes colliding, a nuclear meltdown, or a hard freeze in Texas. Or model very complex systems with many, many, many possible states and all sorts of areas: epidemiology, economics, biomarker discovery. And so these are very complex models, but it's a very powerful tool. So let's get back to the simple. In the simple case, here are the pictures of those 4 posteriors that I had the tables for before. So this is the posterior where the posterior mean was 0.125 and so on. So you see, if you have 0 out of 3 toxicities, here's the shaded areas, what the posterior looks like. And what all of the posterior distribution is, or prior, is something where the shaded area underneath the curve is equal to 1. And I've chopped this thing off at 4 because I didn't want it to go through the ceiling. If you have 1 out of 3, you get this thing that looks like a whale swimming from California to Hawaii. If you have 2 out of 3, the whale's pointed in the other direction, and here's 3 out of 3. So instead of saying 0, 1/3, 2/3, 3/3, you've got a whole probability distribution. Okay. And let's address the issue. What does it mean to say that you've got 33% toxicity? If somebody says this to you, the first thing you should ask them is, out of what sample? If it's 3 out of 9, this is what the distribution looks like. If it's 8 out of 24, which is also 33%, you see it's much more informative. Likewise, 12 out of 36, 20 out of 60 actually gets pretty informative. And all this is saying is that if you begin with this non-informative prior and you observe these numbers of toxicities, you get posteriors that, as the sample size grow, all have got means that are about 33%, but to become more and more informative. This goes along with the notion that everybody should know that as your sample size gets bigger, your estimation becomes more reliable. Equivalently, your posterior becomes more concentrated. Okay, and here are pictures with 95% credible intervals. So here are the things that confidence intervals really want to be. So this is in a case where all the means are 0.67. You see, if you have a beta 4.2, the confidence interval is computed by finding the middle 0.95 area. There's a whole cottage industry in getting credible intervals that are optimal in some sense. They've got highest posterior density intervals and so on. I don't bother with that. If you find the 2.5th percentile and the 97.5th percentile, which you can do in about 10 seconds using a computer program, they're all over the place, you can get the credible interval. And this should be standard practice in the medical literature. You see, for a bigger sample, you get a credible interval that's less wide and so on. So when you get up to a sample of size 48, the credible interval becomes more narrow. Okay, so this is what confidence intervals would like to be. Here, what I've done is add the element that, well, now we've got another variable in play. We've got dose. So it's not just probability of toxicity, it's probability of toxicity as a function of dose. And so there's some model in the background, maybe like a logistic regression model. And you see the distribution of the probability of toxicity as a function of dose marches from left to right. The message here is very simple. All it's saying is that, well, there's a lot of uncertainty with regard to what the probability of toxicity is at any given dose. You know that as the dose gets higher, the probability of toxicity goes up. Okay. Now, here's some Kaplan-Meier estimates of progression-free survival time from real data. We just did a phase 1/2 trial of a targeted agent for advanced renal cancer. We're actually writing the paper up now. And you see that you've got, what, a very tiny sample at 150 milligrams. There were only 2 deaths and so on. And so if you were to say to yourself, well, wait a minute, the 150 is way too toxic, you've got a tiny amount of information. And it looks like 80 and 120 have about the same progression-free survival, but you don't know. So this is the sort of thing that people do all the time. It's not Bayesian. Kaplan-Meier estimates are non-parametric frequentist estimates. And here is what happens when you want to estimate median progression-free survival. In this case, at 80 milligrams, you had 11 patients that died or had disease progression out of 15, and the median is estimated at 6.3. But you have this problem that using the standard formula, you cannot get an estimator of the upper limit of the confidence interval. It's not estimable. So you go to the formula and little NE pops out of the computer. The same thing for the other doses. You had 17 failures out of 24 patients. And so you don't have confidence intervals. So the simple solution to this is don't use frequentist estimators at all. Use the Bayesian model. You have to work a little harder. So we've got two statistics that matter. One of them is the number of events, and the other is the total follow-up time, which is the sum of the times to either failure or the last time you were following the patient and they didn't have the event. And so for the 3 doses, I've given the number of events and the total follow-up time in months. But in the Bayesian world, if you assume a model, will say, well, the mean time to the median progression-free survival time, I'm going to call that mu, follows an inverse gamma distribution. And you needn't worry about that. That's a technical thing statisticians can deal with. But the nice thing about the inverse gamma is that the posterior, if this is the prior, then the posterior is also inverse gamma. And all you have to do is add the number of events to the first parameter and add log 2 times the follow-up time to the second. So again, it's conjugate. So when you've got conjugate distributions, life is easy computationally, although it doesn't matter much these days. And this prior is not informative in the sense that the mean is 10.3 months, which was the guess before you got data. The variance is huge, so it doesn't tell you much. But look, lo and behold, if we compute 95% credible intervals, you see the medians, these are the mean values of the posteriors at each of the doses. But we've got the 95% credible intervals, and they always exist. You've always got a lower bound and an upper bound. This is just the 2.5th percentile. This is the 97.5th percentile. So we have a coherent way to do estimation. After all, in statistics, we've got parameters, and we're always estimating them based on data. So here are the middles or means of the distributions, and here are the 95% credible intervals. And I really think this should be standard practice and should replace what's done in the medical literature, which is this sort of nonsense. Okay, and so here are pictures of the posteriors. Okay, so the 3 posteriors that I got the credible intervals from, I've just drawn pictures of them. And you see that the 3rd posterior is very dispersed because you've got a small sample. Okay, so let's talk about quantifying strength of evidence, which is really one of the important things that we need to get to. I'm going to begin with a toy example. So let's say that we're going to look at frequentist and Bayesian inferences for each of 4 different outcomes of a very simple randomized trial to compare the response probabilities of treatments A and B. I'll call them pi sub B and pi sub A, based on binomial samples. And so you had 80 patients that got A and 80 patients that got B. And in this toy example, I'm going to fix the number of responses for A at 16. So 16 out of 80 is 20%. But for B, I'm going to look at the number of responses being 27 or 30 or 35 or 40. And I'm going to do the frequentist thing, which everybody does, of computing p-values for a 2-sided test of the null hypothesis that the response rates are equal to each other. Okay, so let's see what happens when we turn the crank. So I've got a row for each of the samples, number of responses for B. And here's the empirical estimator of the response rate with B. It goes from 0.34 to 0.50. And here's the difference. Now the pi hat for A is 0.2 all the way through. So all I'm doing is subtracting 0.2 to get to this 3rd column. Here are the z-scores. So everybody, if you taken an elementary, you know how to turn this sort of data into a thing called z, which is an approximately standard normal random variable, and crank out a p-value. So the p-value for this is the probability that a normal distribution is either above 1.96 or below negative 1.96. And it's 0.0498, which is below the magical cutoff of 0.05, which is arbitrary and kind of silly. But let's look at a Bayesian posterior probability, which is a bit more informative. In words, what this thing is saying is computing is the probability, given the data here that we've observed, that the response rate with B is at least 0.20 larger than the response rate with A. And what I'm getting here is that you're testing this null hypothesis against the alternative that B gives you at least a 0.2 improvement. So this probability actually is quite important, because it's how likely it is, a posteriori given the data, that B really gives you a nice 0.2 improvement over A. And so despite the fact that the p-value is significant nominally, that probability is only 0.175. Let's move to a larger sample of 30. You see the p-value plummets down to 0.145. The probability is still not that big. And the first time that you get the probability above 0.9 is if you have 40 out of 80 responses with B for an empirical rate of 50%. Look at the p-value. So there's kind of a disconnect between what somebody would say is nominally significant based on this fixed cutoff of 0.05 and what a Bayesian would compute based on the same data. So if the investigator said to me, I really want to achieve at least a 0.2 improvement, I'd say, okay, I can compute this probability for you. That this is the probability you're getting what you want, but you're going to have 40 or more responses with B compared to 16 responses with A to get that probability large. There is a big disconnect between p-values and just easily understandable Bayesian probabilities. So here's another example. Let's talk about a randomized two-arm study, and the sample sizes are the same. It's perfectly balanced. And we're going to do a one-sided test of whether the two means are equal to each other versus the alternative that the first mean is bigger than the second. And I'm going to fix the variances so we don't have to worry about that, and tell you that the observed z-score was 1.75. Well, we all know that if you do a one-sided test and you look it up in your table or run your favorite program, the p-value is 0.04, and you conclude, quote, mu1 is significantly larger than mu2. So that's standard statistics 001. But what I'm going to do in this toy example is vary the sample sizes. I'll say we've got totals of a total sample size of 20, 10 in each arm, 200, 100 in each arm, or huge, 2,000, 1,000 in each arm. And I'm just going to look at the estimates of the difference, mu1 minus mu2, which is really what we're interested in. So if the total sample size is 20, then the estimate of the difference is 2.48. Here's the 95% confidence interval. If you move all the way up to 2,000, the estimate is 0.25. And here's the confidence interval. So because the z-score is the same in all of these three cases, the p-value is 0.04 in all of these three cases. But notice that the estimators, depending on the sample size, differ by an order of magnitude, from about 2.5 to 0.25. So here's the simple and obvious question. If all three of these data sets have the same p-value, how can a p-value possibly quantify strength of evidence? Here's a significant treatment advance. This is the last toy example, but it's one that's actually occurred many times, or quite a number of times in the medical literature, and it's very embarrassing. You've got a two-sample randomized trial of treatments A and B. Here I've color-coded them. And you're going to use survival time as your outcome. How long does your patient live? And let's say you estimated the A versus B effect to be negative 0.01 in some model, and you got an estimated standard deviation of 0.004. Here's the z-score, negative 2.5. And so the two-sided p-value is significant. It's 0.124. And you can then conclude, as they do in many, many medical papers, A significantly reduced the hazard of death compared to B. Okay, well, let's examine this a bit more closely and assume that the hazard of death with B was 0.2 per month. And if you invert it, you get the mean survival time, which is 5 months with B. This assumes a constant death rate. The estimated multiplicative effect of A on the hazard of death is then the exponent of that, which is 0.99. And so the 95% confidence interval for that effect goes from about 98 to 0.99 and almost 1. And so if you then convert that to a confidence interval for the mean survival time, it goes from 5 months to 5.1 months. So I've very rapidly gone through a lot of technical computations, but they show that this statement up here is ridiculous. In words, it says that A gives a 0 to 3 day improvement in expected survival time compared to B, but somehow that A significantly reduced the hazard of death. 3 days is long enough to say goodbye to your family and write your will if you're lucky. Here's a real data example that a good friend of mine, Pavlos Musal, got out of the literature and showed to me. There was a real randomized trial conducted by ICU doctors to compare two treatments for acute respiratory distress syndrome, which you probably know is what's killing so many COVID-19 patients. And the two treatments were to give ECMO, immediate veno-venous extracorporeal membrane oxygenation, or wait. That is, C is you give them continued conventional treatment, but you allow crossover to delayed ECMO to rescue the patient if they have refractory hypoxemia. So the data that they got were based on a simple binary endpoint, whether or not the patient died prior to day 60. That was their outcome. And fair enough, the data were that you got 42 deaths out of 124 patients, or 35% with the immediate treatment. And you got 57 out of 125, or 45% deaths with the delayed treatment C. So here the outcome is a bad thing. If you do your two-sided test, your p-value is 0.09, which is much larger than the sacred cutoff 0.05, so it's not significant. Again, 0.05 is completely arbitrary. And so in this paper, which was published in the, I think it's the National Enquirer Journal of Mendacity or something like that. Quote, among patients with very severe ARDS, 60-day mortality was not significantly lower with ECMO than with a strategy of conventional mechanical ventilation that included ECMO as rescue therapy. What you're saying is to your colleagues, look, don't bother giving it immediately. Let's look at a simple Bayesian analysis. We're not going to test hypotheses. We're just going to treat the probabilities, as I have before, as random independent variables with non-informative beta priors. And I'm going to compute this very simple probability. In words, this says that if the probability that pi I is less than pi C, that the probability of death within 60 days with I is lower than the probability of 60 days death with C is 0.95, you could say the posterior odds are 19 to 1 that an ARDS patient has higher probability of surviving 60 days if treated with I than treated with C. And the simple question is, if you worked in the ICU, would you bet your patient's life on C, which is to delay the ECMO? Here's a picture of the distributions. Remember, Bayesians consider parameters random, and we can draw their posteriors. Here they are. Notice that the mountain for the death rate with C is to the right of the mountain for the death rate with I. You can draw your own conclusions based on this analysis. Look at the 0.95 and say, is that big enough for me to use I instead of C? It's up to you. Okay, so back before the pandemic, I actually had an office where I sat at a desk, and I do vast amounts of consulting with the physicians at MD Anderson. That's my whole life. And I asked some of them as they came into my office, I'd like to know how you define p-value. After all, your papers are full of p-values. Here's one. The probability that E is not better than S is less than 5%. Second, something that represents significance and that occurs when the p-value is less than 0.05, rather circular. P-value less than 0.05 is the observation that a particular event studied has less than, it just goes on and on. And then the probability of inappropriately accepting the null hypothesis. The actual definition is that it's the probability under the null hypothesis of observing a value of the test statistic as extreme or more extreme than the value actually observed. And I'm not going to go through this technical computation. There's software that does that. But the point is that these statements came from very intelligent people that have been doing research for years. They just don't know what the definition of a p-value is. Okay, so p-values are misused all the time, and I've made a kind of a laundry list of how they're misused. They're misused, first of all, to quantify strength of evidence. That's absurd, as I showed you by example. And here's the big one. It's confusing a p-value which is below 0.05 and calling it statistical significance with practical significance. And the question is, what's so sacred about 0.05? The fellow who invented modern statistics in the early 20th century, Ronald Fisher, was asked when he cooked these up, well, how small is small? And he says, oh, I should think that something that happens less than about 1 time in 20 ought to be considered meaningful. And then the fact that you dichotomize your evidence, you say accept or reject, regardless of sample size, estimated effect size, or how many p-values you computed. Publication bias is due to studies with insignificant p-values being less likely to be published. Editors do this all the time. Or a researcher cherry-picking significant p-values from a set of many computed p-values of tests for repeated repetitions of an experiment. Just keep doing it until your data give you a p-value less than 0.05. Or just keep looking at subsets of your data until you find a subset with a p-value less than 0.05. Or different outcomes. Do a test for response, a test for survival, a test for progression-free survival, and so on. Every one of those tests has got a p-value. Or if you've got multiple covariates in a regression model, just do a test of whether the parameter for that covariate is 0. If you have 20 covariates, you should expect, on average, one of the tests to be significant, even if it's pure noise. I've got a whole chapter in my book talking about p-values and a lot of the ridiculous problems you get into with them. Some journals have taken the action of banning p-values, which is probably not a bad idea. So I'm going to shift gears now and look at 2 outcomes. So one of the things that I've been working on for the past 30 years is how to evaluate treatments. In fact, how to make decisions during dose-finding trials or randomized trials based on multiple outcomes. And the simple version of multiple is 2. You've got efficacy, which is in blue, and toxicity, which is in red. Here's a table of probabilities. And so here we're assuming that we know the probabilities. So I'm giving you an example. And the probabilities in these 4 cells, which are the 4 possibilities, you don't have efficacy or you do. So efficacy is like 50% tumor shrinkage or what have you. And toxicity either occurs or not. So they're simple. 2 times 2 is 4. And here are their probabilities. They have to add to 1. But the marginal probability of toxicity is the sum, 0.25 plus 0.05, which is 0.3. And the marginal probability of efficacy is also 0.3. Okay, so that's at dose 1. Here's the same sort of thing at dose 2. And you can say, well, dose 2 is higher or something like that. And what I'm doing in this example is saying the no toxicity probabilities are the same, but the toxicity probability, the efficacy probability went up in the toxicity row. So in this, for dose 2, the probability of efficacy and toxicity is 0.25. And what happens is the marginal probability of efficacy goes up to 0.5. So now we're in the dose comparison business. We have to choose between dose 1 and dose 2. Of course, in a phase 1 or phase 1/2 trial, you've got many doses, but here's just 2 of them. Well, if you just stare at these marginal probabilities, you'd say, well, the toxicity rates are the same. They're both 30%. Dose 2 has got a higher response rate, so dose 2 wins. But that's not what people do. If they just base it on the probability of toxicity, they'd say they're equivalent. And by the way, every single phase 1 trial design that only uses toxicity to make decisions is doing exactly that. It's ignoring efficacy. So every phase 1 trial design in existence would say that dose 1 and dose 2 are perfectly equivalent. And moreover, if you are an optimist and you say, well, I want to look at the event, I'm going to account for efficacy, and I'm going to look at the event of the best possible thing where you get efficacy and no toxicity, but for both doses, that's 0.25. So once again, they're equivalent. Whereas if you look at the entire distribution, the message is no, dose 2 is better. So all that I'm saying here is that when you're looking at 2 outcomes, you really need to look at the entire joint distribution. And a lot of the things that people do just don't do that in dose finding trials or when they analyze data. Okay, so let's talk about utilities. What are utilities? Well, here's the basic idea. I've got the same sort of thing. Now I'm using response instead of toxicity, same thing. And I'm going to assign utilities to those 4 outcomes by saying, well, the best possible thing that can happen is you get a response and no toxicity. So I'm going to give that the maximum value of 100. The worst thing that can happen is the patient doesn't respond and has toxicity. I'm going to give that a utility of 0. And so then I'm going to have to elicit 2 more utilities, and I actually do this. I sit down with my MD collaborators and I ask them, how good are they? So I give them this table where there's 100 here and a 0 here, and I say, well, compared to that upper limit and that lower limit, if the patient has doesn't respond, but they have no toxicity, what's the utility of that? It obviously is higher than the 0 because no toxicity is better than toxicity in this row. Likewise, what's the utility of having response with toxicity? So if you get up 100 having a response with no toxicity, how much does that go down if you have a toxicity? All this is, so once I get these numbers, now I've got numerical values that quantify the risk-benefit trade-offs for the for outcomes. And we do this all the time. I do this routinely now. So here's an example where we've gotten the utilities. And so the utilities are 0 and 100, but 40 for nothing happening and 70 for having both events. And I've actually put in probabilities. I'll say, let's assume we know them. And in real life and during a trial, what we actually do is we estimate them. But let's suppose those probabilities are 0.4, 0.1, 0.3, 0.2. Then I could compute the mean utility. All I do is take the weighted average of these utilities, where the weights of the probabilities, and I get the magic number of 60. So if I do this for each dose, then I can compare the doses based on their mean utilities. We've been doing this for about 10 or 15 years now at MD Anderson. Okay, so here's how we do utility-based Bayesian sequentially adaptive phase 1-2 trials. The goal, given some doses of some agent or regime, which could be, how much radiation therapy do you give them? What's the dose? Based on efficacy and toxicity, we want to find a dose that maxes out the utility. The decision criterion is based on the elicited utility. And for each new cohort, we select the dose that maximizes the posterior mean utility based on the data. We also do this thing, we randomize among doses that have posterior mean utility that are close to the max. If you don't do this, you could possibly get stuck at a suboptimal dose. And we've got these rules. We say, well, marginally, you've got to have acceptably low toxicity probability and acceptably high efficacy probability. And then if no doses are acceptable, you stop. Okay, so here's a real trial that we did in a horrible brain kind of disease, brain tumors that are diffuse intrinsic pontine gliomas. They're very aggressive. The median age of the patients is 5 years, and you actually get infants with this disease. There's no treatment with any substantive anti-disease effect, and median survival is less than a year. So radiation therapy is the standard treatment, but it's primarily palliative. So the radiation dose toxicity and dose efficacy profiles were not well understood, and they wanted to evaluate 3 doses. Okay, so toxicity was defined on an ordinal scale as mild, moderate, high, or severe. And we began with 3 levels, and then when we started staring at it, severe includes things like blindness and death. So we made it more refined with 4 levels. See, I talked to the PI, Anita Mahajan, and said, well, we need, good things. And so she said, well, there are 3 good things, that they're improvement in clinical symptoms, improvement in radiographic appearance of the tumor, or improvement in quality of life. And so if you just give each of these a score of 1, you could get 0, 1, 2, or 3 improvements. And both of these were scored within 42 days. So 4 times 4 is 16, and that's how many elementary outcomes we had. Here are the actual utilities that I elicited. So we began with the 0 and the 100, and I elicited these numerical values. And there were actually a couple of physicians involved, and playing around a little bit, we talked about it. These numbers are what they came out with. Notice that the values get smaller as you move from lower left to upper right, as the toxicity gets more severe and you get lower efficacy. Here's a picture of the utility function. This is just to show I know how to make plots in PowerPoint. So the first question is, well, why bother with all this? Why bother with utilities? What a pain in the neck. If toxicity is defined to say, lower moderate is acceptable, higher severe is not, just why not say dose limiting toxicity is higher severe and make life simple? And use a 3+3 algorithm, or maybe the continual reassessment method. Why use this fancy stuff? The answer is, if you write out the table of utilities, you see that the utility of no responses and moderate tox is 0.25, and the utility of 3 responses, which is the highest, with high toxicity severity is the same thing. So these two outcomes are equally desirable. So scoring these, one of them is no DLT and the other is DLT, makes no sense. The point is, all we're doing is taking the subjective thinking that all physicians go through and formalizing it. That is, all I'm doing here is giving structure to the way that physicians think. And I find that all the people at Anderson that I work with, where we use utility-based designs, love this, because it's as if they've been waiting forever for somebody to ask them what their utilities are. But this shows you why it's better to use utilities than not. So here was the trial. There was an accrual rate of 6 to 10 per year, sample size of 30 max, cohorts of 3. We started at the lowest radiation dose. There were 3 of them in terms of biologically equivalent dose, and we couldn't skip the middle dose when escalating. And then we had these rules that said the probability of toxicity, it was unacceptably toxic if the probability of toxicity being high or severe was bigger than 10%. And there's the formal statement of it. And here are results of a simulation study. We always simulate these designs because you don't know how they're going to behave. This is something which is along the lines of somebody giving you a size of 0.05 and a power of 0.80 and a test of hypotheses. This is much more structured. Here I'm simulating the trial under a bunch of different scenarios. In the first scenario, what I'm giving you is a plot of the utility, the percent selected patients, and the number of patients. And see, you see doses 1 and 2 really have the same max utility. Most of the patients are treated there. And, most of the selections are there. Here, the third dose, the highest dose has the highest utility, and it's selected most of the time, and so on. So what we do is simulate the trials to see if they work well. And if not, we tweak the design parameters and then resimulate. And we may go through 2 or 3 rounds of that. I'm not going to go through all of this except to say, here's a case where no dose is acceptable, and the design does a good job of stopping and saying no dose is acceptable. Scan the trial. Okay, so here's another example. This is a randomized trial to compare nutritional rehabilitation to standard of care in terms of their effects on postoperative morbidity for patients undergoing esophageal resection. And so the goal is to compare new prehab and to standard of care, but we want to allow different conclusions in 2 subgroups, primary patients and salvage patients, which is called precision medicine. So postoperative morbidity score is 0, 1, 2, 3, 4, or 5, where 0 is normal recovery, 5 is death. Physicians, the surgeons use this all the time. And the sample size, we began with 100, but Wayne Hofstetter, who was the PI, got other institutions. We got it up to 200. And it's taking quite a lot more than 2 years as usual. And we're randomizing and doing an interim look at 100. So here are the elicited mean POM scores. So all this is saying is that I'm getting the probabilities that are used to construct the prior, but here are the elicited utilities. So for a POM score of 0, it gets 100. For 5, which is death, you get a 0. And here are the utilities for the in-between values. You see there's a big drop off from a POM score of 2 to a POM of 3. So there's our utility. And so we've got a rather nicely structured Bayesian model, but the decisions are based on this posterior probability, all right? And in words, what this says is that if the mean utility of new prehab is likely to be larger than the mean utility of standard of care in subgroup G, which is either primary or salvage, given the data, then you conclude that N is superior to C in that subgroup. And then you've got the symmetric rule where you reduce the roles of N and C. And we simulated the design to see what its properties were, and here's what we got. So we've got 4 scenarios for primary and salvage, and in the first case, there's no difference in either subgroup. And so the probability of concluding N is superior to C is small, and so you get a type 1 error, which is smaller than 0.05. And the probability, again, of concluding N is inferior, these are symmetric. is small. Now, case 2 is interesting because now we've got a subgroup effect. So in this case, in the primary patients, you've got a new prehab effect, but in the salvage patients, there is no effect. And what you see is the design intelligently picks that up in the subgroups. So it's able to say, with probability about 78%, yes, there's an advantage to giving new prehab, but it's very unlikely to make that incorrect conclusion for the control patients. And then if you reverse it, you get the same sort of thing. Here the power is, probability is 0.81. And then if you have an advance in both subgroups, you go, wow, it's above 82 or 85%. So the design does a good job of subgroup specific decision making. And we started doing this. That is, we started saying, well, if patients are heterogeneous, let's have our decision making subgroup specific. Here's the case where we're going to use the design that ignores subgroups. So here's the design that somebody would use if they didn't distinguish between primary and salvage patients. And you see that you get a higher power figure. That's the price you pay. But look at scenario 2. Let's look at what these values mean. So the probability of a type 2 error in the primary group, which is a false negative, you missed in advance, is about 56%. And the probability of type 1 error in the salvage, which is the probability you wrongly conclude there's an advance, is about 44. And so all this says is you might as well, if there really is a treatment subgroup interaction, you might as well just flip a coin instead of running a trial, because these error probabilities are huge. And so what's going on here is that this says that probably in thousands and thousands of clinical trials where there was heterogeneity and the design didn't account for them up front, there's a huge risk of making these immense subgroup specific incorrect conclusions. And the way people get around this is after they get the data, they go looking at different subgroups and estimating things. But there, basically, you can be accused of data dredging. All I'm saying is, if you believe that there is likely to be heterogeneity, go to the extra work of accounting for it up front to avoid having these horribly high error rates for the subgroups. So here's Bayesian inference. This is for observational data. So this is a rather specific area where Bori Anderson had cooked up this thing called pharmacokinetically guided versus fixed dose intravenous busulfan in allogeneic stem cell transplantation. So allotransplant is the established regimen for advanced hematologic malignancies. It's way better than chemotherapy, and it includes myeloid leukemias, myelodysplastic syndrome. And so for the preparative regimen, IV busulfan plus fludarabine, the delivered dose in terms of systemic exposure is quantified by the area under the curve that you get from doing a pharmacokinetic analysis. So AUC is the delivered dose in the blood. It's well known, or it's been established, that if the AUC is too low, you get a high risk of graft failure or disease recurrence. If the AUC is too high, you get high risks of toxicity to graft versus host disease. So it implies that there's an optimal middle AUC interval. And Dr. Anderson knew this, but he didn't have any way of quantifying it. He gave me some data and I drew this curve. So what you've got on the vertical axis is the risk of death. And this shows that there's a middle range where the risk of death is lower. The risk of death is high. Here's the AUC dose on the horizontal. If it's too high you get a higher risk of death. If it's too low, you get a higher risk of death. So there's kind of a sweet spot in the middle. And believe it or not, based on this one simple little graph that it took me about 5 minutes to draw, for many, many years, they've been using this interval to get a small pre-therapeutic dose, get the patient's pharmacokinetics, and then choose their optimal dosage interval in these units. I won't get into the details. So we've had about 2 decades of that. So here's a picture of some data. We got 218 patients who were randomized to fludarabine, fixed dose IV BU, 107 patients, or PK guided IV BU. And you see that the PK guided gives you a higher survival. So using the pharmacokinetically guided dosing improves survival. And this has been known for a long time. I apologize for using p-values. If I did it today, I wouldn't. So if we fit a Bayesian piecewise exponential regression model, which includes not just the PK guided dose, but age and whether they were FLT3 positive and so on, then we can, for the parameter multiplying each covariate, we can compute this formula, which is the posterior probability of a beneficial effect. That is, if the variable takes on a value of 1, or if it's larger numerically, then that higher value of the variable is beneficial. And the piecewise exponential, here's a picture of it. It does a great job of approximating any hazard. That's technical. But here's the fitted model. And all I've done for PK guided versus fixed dosing, you see the probability of a beneficial effect. Now we're Bayesians is 0.92. For age, the probability of a higher age being beneficial is 0.03. This says the probability of a harmful effect for older age is 0.97. We all know that the older a patient gets, the worse it is. One of the things that's poor cytogenetics, the probability of a beneficial effect is 0.02. The probability of a harmful effect is 0.98 and so on. So these are the things that I compute when I fit these regression models. They're Bayesian. And I use these instead of p-values because p-values are frankly misinterpreted and they don't mean much. Whereas the probability of a beneficial effect is a Bayesian posterior probability, which means exactly what it says. So the probability of being in complete remission at transplant being beneficial given the data is 1 to 3 decimal places. Being FLT3 positive turned out not to matter. So if you had a value of 0.5, you'd say you're right in the middle. It's complete noise. Values near 1 are great. Values near 0 are bad. Of course, you can't control age. The only thing you can control is treatment. Okay, and here's a picture of the posterior distribution of the parameter multiplying the indicator of getting PK guided dosing. You see this area here is 0.922. So we do this when we analyze survival data. So I didn't know that I have time for this, but let's actually go through it. This is a trial we're running right now. So one of the stem cell therapy people said, well, I want to use Treg cells for ARDS for COVID-19 patients that have been intubated. So this is, last ditch therapy to see, can you save them? So we've got 3 arms and one of the arms is a placebo, just saline injections. And then you're going to evaluate, you're going to give this to them on days 0, 3, and 7. And these patients have been intubated. Okay. So arm 1 is just saline injections. Arm 2 is 100 times 100 million cells. Arm 3 is 300 million cells. And the rationale for randomizing is that there's no reason to assume that either the probability of toxicity or the probability of response increases or decreases with Treg cell dose. You get this non-monotonicity with cellular therapy because they don't know. And randomization gives unbiased comparisons. Okay, so there were 2 co-primary outcomes. The thing I call TOX2 is regimen-related toxicity, grade 3 or worse within 2 days of the first infusion. A28 in blue is that they're alive and not intubated at day 28. And then there are a whole raft of secondary outcomes. With the baseline covariates include age, gender, whether they need a vasopressor, and so on. Okay, so we're doing a balanced randomization where they've got up to 45 patients, which is, it's a pilot. And at the first interim look, I restricted it to be perfectly balanced. So there are 5 patients in each arm. At 30, there are 10 in each arm. And at 45, there are 15 in each arm. If you don't restrict it, you get unbalanced sample sizes. So that's a statistician's thing. And then the FDA rule said we had to stagger patients. Although the FDA review said you had to stagger patients, but didn't say what to do during the extra wait. So it was kind of silly. So here, they needed a stopping rule. So this is what I was getting to. So I'm going to call PTOX2 the probability of this toxicity event, and 0.4 is the limit. So if the probability of TOX2 being bigger than 0.4, given the data, is large, bigger than 90%, you don't enroll to that arm anymore. And so here's a table where we simulated it, and I just got the stopping probabilities, assuming true PTOX values from 0.4 to 0.7, and you see the stopping probabilities go up. So if the tox rate is really 0.7, the probability will terminate the arm is 71%. Now we'd like this to be large. We'd like it to be 90, but we've only got a tiny sample of 15 patients. So the rule does pretty well. Okay, so that's, I think, the early stopping enrichment. I won't get into that. All this says is, very briefly, without reading it, if you terminate one arm early, don't say, yay, we've got a smaller sample size. Enrich the arms that are remaining. It's a much better way to do it. I know I've covered a lot kind of rapidly, but any questions, comments, accusations?
I'll ask one, I guess. Any situations where these Bayesian methods are not appropriate?
Well, it depends. I mean, I began using more and more Bayesian methods. Now I use them almost exclusively, except for, Kaplan-Meier plots, which are nice. I don't know. Any place that you can use a frequentist methodology, you can use a Bayesian methodology. Bayesian methods are especially useful when the sample sizes are small to moderate. If the sample sizes are very large, it doesn't make much difference whether you use a Bayesian or frequentist methods, except that there are many examples where with a large sample, the frequentist methodology led you to the wrong conclusion. I don't have time to get into all of that. And what that comes down to is the general rule that because Bayesian inference is based on the posterior, which essentially is an average between what you see in the data and what you assumed a priori. So you've got a bit of shrinkage. You get more sensible posterior inferences. So I'm so used to thinking like a Bayesian that frequentist methods don't make much sense to me anymore. The other thing I noticed this 25 years ago, 30 years ago, is that almost all the physicians I worked with actually were Bayesians. They just didn't know what the statistical technology was. And I had to develop this whole array of Bayesian designs over the years to do what they actually needed done. So that's sort of the long-winded answer. There are methods out there. I'm not going to badmouth all of them.
And then can you just speak, I know you touched on this a lot in your talk, but when you really don't know prior probability estimates a priori and how you handle that with these methods?
I just assume a non-informative prior. So for example, say I'm fitting a regression model. The regression model has got these parameters that multiply the covariates. You've got the parameters are, some intercept beta naught plus beta 1 times age plus maybe beta 2 times the treatment effect and so on. So those betas are parameters. And I just give them normal distributions with very big variances, like a normal with mean 0 and variance 100, so that the prior is not assuming any information that you don't have. And with the way we quantify that, we figured out years ago, you can quantify the information in a prior in terms of its effective sample size. So if you tweak the variances, so the effective sample size is around, a priori is about 1, now you've got a prior. And so the prior is not getting in the way. That is, we never use priors that are informative when we don't have actual information. And that gets into a physician who's highly opinionated saying, here's my opinion, I've got an informative prior. And that informative prior really affects your posterior inferences. So what's happening is strong opinion is affecting your inferences. And there you've got a problem. The way out of that is to do the analyses with, say, 3 priors. Have a prior that's optimistic, a prior that's sort of in the middle, and a prior that's skeptical. And then for every one of those priors, you compute posteriors and you form your inferences. You say, here are our conclusions if we begin with an optimistic prior. Here are our conclusions if we begin with a prior that's sort of in the middle. And here are our posterior conclusions if we begin with a prior that is not informative at all or pessimistic. And you can make a whole array of different priors and then let people look at how each prior drives to a set of posterior inferences, and then they can form their own conclusions. So this is called a prior sensitivity analysis. When you analyze data, you're not married to one prior. You can analyze the data using several different priors to see what you get.
This
All
is
right.
just more of a comment, but as you know, we're disseminating these lectures to residents throughout the country, and I've been trying to raise a little bit of awareness for some resources that are resident-friendly for statistics, and I wanted to let everyone know that you have written a book called Statistical Remedies for Medical Researchers, which I think you briefly mentioned, but
Yes.
it is written to be accessible for non-statisticians. So.
Yes, yeah, I spent a lot of time and effort on that book. It's got some technical content, but both of the reviewers were statisticians, and they both said it was verbose, which I found amusing because I did not write it to be written in that tight mathematical style. I wanted it to be readable by physicians that do medical research. That's my target audience. When I talk to physicians that I'm working with, I begin explaining something and I say, well, if you just buy my book, this is explained in chapter this or chapter that.
Terrific. Well, thank you again. I want to thank you for taking the time to do this. I know this was helpful, and I think it will be helpful for other residents who tune in on the webcast after the fact. So thank you again, Peter.
Okay, thanks for inviting me.